Okay, thank you, Shazia, and thank you for having me. It's really, of course, my pleasure to be here, and indeed to add University of Queensland to the places I have visited. Very nice, so thank you for the invitation. So this is a tutorial about data profiling. Shazia had asked originally in the invitation, do we want to give a talk, or is this tutorial style of things? And I thought, well, why not a tutorial? My main goal for today is not that you become experts in data profiling. I think the kind of research we've been doing in this area might be a good example of how to do, I'm not going to say good research, but how to think about problems. So my goal here is that you get some ideas about how to go about designing algorithms, how to go about designing data structures. So, don't worry about the data profiling as such, but hopefully enjoy the nice ideas that I hope I will be able to present to you today. And just like Divesh said, you're very welcome to interrupt me with questions, even more so in a sense because it's a tutorial. So the goal is really that you hopefully learn something. Okay, so please interrupt me. I do have one slide about HPI, Hasso Plattner Institute, just because it's not quite as known as maybe AT&T or UQ. So Hasso Plattner is a co-founder of SAP. He's like the German Bill Gates, you can think of him that way. And he founded this institute, has put over €1 billion into this institute already. We have about 25 professors. We have a campus much smaller but equally nice, as you can see, also students sitting on the grass and studying, just like I saw for lunch today. And we're in Potsdam, and Potsdam borders on Berlin. Actually, I can tell you at least that these trees here are already in Berlin. So if you're interested in visiting Berlin, do stop by at HPI and let me know. Okay, good. So how did I start this kind of research? It was really long ago. In 2005, I had a great young PhD student, Jana, who was working mixed in the area of life sciences, databases for life sciences and data integration. And we had this vision at a CIDR paper in 2005, hands-off information integration, right? And so we put together this pipeline. We have all these different sources, and then you need to figure out how they belong together, right? This is this inclusion dependency discovery that tells you how can sources fit together. You do that within a source, you do that across sources, and suddenly, as if by magic, you're able to integrate the databases. And we kind of got stuck right here at the very bottom because it turns out those kind of problems are already very, very complicated. And this is what I will be talking about. I mean, the community is very, very far from almost hands-off information integration. So there are many, many tools, but they're very much hands-on tools, I have to say, right? But we will be, I'll be presenting kind of one ingredient in the information integration process. I also have this nice citation. This is, 7 years later, by all these famous researchers who identified, many different, also kind of grand challenges in database research. And one of them basically says, well, if you have a bunch of data sets, think data lake, yes, then all of this is useful if you don't have adequate metadata. So data profiling is about extracting metadata from data. Here's a big table, extract some metadata, right? And what kind of metadata is what we'll be defining throughout the tutorial. So think of it in this way. You have a bunch of data sources, and there's lots of technology already to prepare the data. We heard about this morning already by Shazia. Data integration, data exploration, cleaning, data preparation in general, then to serve all these different applications, data mining, analytics, optimization, AI, machine learning, etc. Right? And the idea about data profiling is that before you start on this journey, you extract a bunch of metadata automatically, and all this metadata will help you perform preparation, will help you run your applications, optimize your systems. This is the very general and broad idea, and you can already see here abbreviations for the kinds of metadata that we'd like to extract. So this is a functional dependency, an order dependency, unique column combination. These terms will come again and again, and I'll define them, of course, right? So this is the big picture, and I've split this tutorial into 3 parts, each 40 minutes, so bear with me. There will be breaks in between, and by you asking a question, that's implicitly also a little bit of a break, right? So do go ahead and ask if you don't understand something or you have a comment. You're very welcome. right? So the first part is kind of the easy part. This is introduction, motivation, what is all this about? I'll define what data profiling is, which tasks we want to solve, and why this is difficult. The second part will be the algorithmic part. I'll show you a whole bunch of algorithms to perform data profiling. Again, think of these as, don't think of it as an exam and you'll have to be able to repeat this exact algorithm, but I hope to bring across some of the key ideas of why this algorithm is a good idea, right? And which techniques we're using, okay? And then the last part is dedicated to applications and use cases. So what can we do with all this metadata that we have looked into? Okay, this is the broad structure. So let's dive right in, unless there are questions so far. Okay, cool. So this is the overview for the first section here. Motivation. I'll give you a list of tasks. I will show you some of the tools that are out there, and I will tell you why they're not adequate, why researchers need to do some research to make them better. And then we'll already start a little bit into this area of basic statistics, like counting the number of rows in a data set. That's also profiling. It's a little bit easier, right? But you need to do this as well, and I'll be talking a little bit about this. Okay? So I'm sure many of you have downloaded a, let's say, CSV file or an Excel table from the web, and you open it, and that's how it looks, right? So who's done this kind of thing? I mean, I'm sure all of you, exactly. So what do you do with this file? So your boss told you, here's your data. You open it. What do you do? What do you do? I mean, literally. How do you go about it? Go ahead.
Maybe check if it is what I expect and check the quality of it.
Okay, exactly. Yeah, kind of explorer. You browse around a little bit. So if it's the kind of stuff you expect, you might be looking at the columns and saying, are the headers, is this for you? Is this first name, last name, or what is this, right? That's already some kind of a good indication. Us database people have one other thing that we do immediately after we open a file like this. Any ideas? Or what will you guys be doing? Go ahead.
We check the statistics of the data, each column.
Yeah, okay. Even easier. I completely agree with you. Even easier.
I would save the raw data.
Huh?
I would save the raw data.
Save the raw data? Okay, before Excel does strange stuff to it. Yeah.
Missing values.
Look at missing values. You can already see, suspicious gaps here. Absolutely.
Check the structure of the table, like what columns.
Yeah. What columns? Exactly. That's all absolutely right answers. What? Exactly. This is what at least we database people do. How big is the file? You scroll to the bottom and figure out how many lines do I have. Is this a big file or not, right? This is like the first thing, at least I always do, right? It's the most basic statistic, but obviously it's important, right? And you need to know about these kind of things. And then I agree with all of you. So you can do, if you just want to explore, Excel, if you start, creating a filter, it will tell you, the number or the distinct values of that column. Implicitly, it's not really profiling, it's just a feature of the tool, right? And then you can go a little bit further, and for instance, in this case, I removed the W for the race code, so I removed, I guess, all the white people here, and then you can go ahead and count, and then you see how many non-white people are in this particular data set. So that's already a little bit of statistic, not systematically, but it's kind of an exploration, right? What is my data about? Who said null values? Somebody said null values, there you go. So that's a nice thing. If you zoom out in Excel, you can do a bit of profiling, right? You just zoom out, and then you can see patterns, right? And in particular, patterns of missing data. So I would argue, actually I have a pen, let's see if I can see this. I would argue if data is missing here, it will also be missing here, for instance. That's kind of a pattern, right? You can also see patterns of the lengths of data. So if sometimes you have might be maybe a suspiciously long value or suspiciously short value, these kind of things, you can do visual exploration. Okay, so this is easy. These are easy things, but of course we want to go beyond that. We want to do some more systematic profiling and tackle some of the harder problems, not just looking at the data. Right? But this is already important. Okay, so what is data profiling about? So first of all, what I'd like to distinguish is single column profiling from multi-column profiling. Single column profiling looks at one single column, or at each column individually, and does exactly what you guys said. How many null values? Is there a pattern in that column? Are there data types, et cetera, et cetera. So it's, as I said, the most basic form of profiling. And the assumption kind of is, or your hope is that all the values in one column are of the same type and have some common properties that you'd like to extract. Right? If you already fail at that, if your data is wild, you have phone numbers and last names and dates all in one column, you can find that out as well, but it will be more difficult to find out nice metadata about it. But so you probably have data errors. Go ahead.
So even if a column has values of the same semantic type, syntactically they might look quite different.
Yes, so you could have last names that are short and long. You could have dates that have different formatting, right?
Phone numbers in the US and Europe with different lengths.
Right, different length phone numbers. Absolutely, absolutely. So we'll get to that. Exactly. So we have to look at structure and semantics. I actually have a slide about that. What kinds of metadata do we want to extract from one single column, right? Absolutely. Okay. This is stuff that is usually also done by database systems, right? If you load a table into a database system, that database system will usually gather some basic statistics like the number of unique values or value distributions, these kind of things. Okay. Multi-column profiling is, to me as a researcher, more interesting because it's not just about counting things, it's more about discovering things. So we want to discover joint properties, properties that are true across multiple columns. And this makes life much more difficult because you have a whole bunch of columns and you have to suddenly look at column combinations, right? And as a computer scientist, at least, the word combinations is like a red flag, right? Because there are many combinations, yes? So in particular, we want to discover dependencies. I'll show you what kind of dependencies we have. And so suddenly the complexity is not just in the number of rows, right? It's in the number of columns as well. And in database research, we're all very, very much used to this kind of complexity. All database systems can easily handle very large data sets in terms of number of rows, right? There's specialized algorithms, indexing, distribution, all these kind of things. What computer science is not, or database systems are not quite as used to, is complexity in the number of columns or in the number of column combinations. So this is what makes it a real challenge. So this is a citation from Ted Johnson, who works as a colleague of Divesh, works at AT&T, who's also worked in data profiling and defines data profiling refers to the activity of creating small but informative summaries of a database. Okay, this is nice. And so I've listed some concrete tasks. So single column tasks might be cardinalities. So how many distinct values do I have? The uniqueness, is my column unique, yes or no? Is it maybe a key candidate, right? Then patterns, as Divesh said, maybe regular expressions, data types, this kind of thing. Then value distributions. Then domain. Can I say this is a phone number, this is a date, this is a first name, this is a last name? Can I distinguish phone numbers from fax numbers? These kind of questions. Okay. Yes.
So do you explicitly include the idea of sampling as a profile for a column? I don't see it explicitly listed.
So it depends on what you want to do. So sampling is I could take a 1% sample of my data, and then your question is that already, have I performed data profiling? If I look at the sample, is that a nice summary of my data?
Small, it's informative.
Yeah, well, okay, I would argue, is it informative? I'm not quite sure, right? It's still a bunch of values, so it's not a summary of sorts. It's a subset. So, but I mean, of course, I'm not explicitly excluding anything. If you like to do that, Yash, you're very welcome to. Of course, many of the techniques we will look at rely on sampling so as not to have to read all the data, right? So that is clear. So we use sampling all the time. Is the sample itself already, a metadata? This is maybe a philosophical question. So take a good example from Divesh. He's asking questions. Please do as well, right? Sometimes I have the tendency to talk fast, so do interrupt me. Okay, and so multi-column tasks, which don't worry, I'll define soon, are things like this. So the uniqueness, not of a single column, but of multiple columns together. So for instance, is first name, last name, date of birth, is that unique, yes or no? Okay. Then so-called inclusion dependencies are the values of one column included in the values of another column, okay? And this is needed to connect two tables maybe as a key foreign key relationship. Then you need an inclusion dependency. Then we have so-called functional dependencies. I'll explain this later. And then there's lots of other stuff like order dependencies and denial constraints, et cetera, et cetera. In the course of the tutorial, we'll only look at, in the next section, we'll only look at those three as, let's say, the canonical kinds of dependencies that we want to discover. Everything beyond that is, I'm going to say, just more advanced stuff that we don't need in this tutorial. Okay, so brief definitions. So unique column combinations, or UCCs, or just uniques, right, are column combinations, sets of columns of size 1 or larger, right, for which we have only unique values or unique value combinations. So first name, last name, phone number might be unique. Social security number alone might already be unique, etc. Okay, so they are a prerequisite for keys. So if you have a big table and you're wondering what could be the key of this table, because you want to index it, you want to load it into a database, you want to understand what is this table about, in a sense, right? Then you're looking for keys, but if you don't know what the key is, you have to find unique column combinations, and among those, choose the one that is the key. The primary key, right. But you might also be interested in secondary keys, other keys. It's also interesting. Okay, so functional dependencies are values of, basically state that the values of one column determine the values of another column. They indicate redundancy in data. So the common example is zip code determines city. So if you know the zip code of some address, then that already determines the city. Usually, maybe not always, but in general. Go ahead.
Sorry, just to practice that roughly like association rule mining, where you could, I mean, that's then the full support, but you could also argue that at least is quite determinant of another.
Yes, exactly. You could think of this as an association rule with high confidence. And, exactly. Although, with 100% confidence, 100% support. Yes, it's an extreme case, if you will, right? But these things do exist. So association rules are, let's say, a more brittle thing, and you can always discover something, but functional dependencies are, in a sense, a very strict form, but they are also present in data quite a lot, actually, right? And as I said, they indicate redundancy. So if you're into machine learning, for instance, you could argue, if you find a functional dependency, you might as well not use the dependent column as a feature, because it's dependent on another column. It doesn't add information, right? That would be a way of thinking about this for a machine learning. And then finally, inclusion dependencies. As I said earlier, all values of one column are included in the other, or all tuples, all value combinations of one column combination are included in this other column combination, right? And as I said, it's a prerequisite for a foreign key. So you usually look for inclusion dependencies across two tables, so that you can say you can join one table with another table based on the two columns that are included in one another, okay? We'll look at examples later. Okay, so just so you know usually what I'm talking about. And then one big question, it's really, I'm not gonna say it's an open research question, but it's something that people have been struggling with a lot, is the question of which of the dependencies that we discover are in fact genuine, meaning they are not only true for the instance, the table I have here, but they should always be true for this table, okay? So because all the discovery that we're gonna be doing is on a given data instance, a table. Okay, or a database. And you're going to discover lots of stuff that might be accidentally true. It just happens to be true for that database. Could be even an empty database, then in a sense everything is true, right? But we want to find things that are genuine or true. So this is something that a human expert, in a sense, can only validate, right? So there might be many possible keys, and they all look nice. They all have the key properties. They're all unique. But it's very difficult for a computer to automatically say, okay, this one is the primary key, right? Of course, but there are methods that try this and they support users, but in the end, of course, it's really a human decision because it's a modeling decision, right? So, but I mentioned this explicitly because we always have to keep in mind all of the nice discovery and profiling we're doing, and we're calling it dependency, but it's really not a dependency. It's a property that this data instance happens to have at the moment. It looks like a dependency. Maybe it's always true, but right now I can only see this particular data set. But they're still useful, right? So if you have a significantly large data set, what you discover there is not unlikely to be true also, tomorrow and the day after. Okay? But it's an important part. And I do get, sometimes when we submit papers, I get complaints about this, saying, you're not discovering dependencies, right? Because a dependency is a general statement, and we're only discovering things on one particular data set. Okay, so these are, in a sense, strict definitions. We'll do the more formal definitions in the next section. But people have discovered that data is dirty, right? And Shazia will be able to say this, and you all know that data is dirty. So what research has come up with is this concept of a relaxed dependency. So relaxed dependencies are those that do not necessarily need to be always true. They need to be true most of the time or much of the time, right? So there are many different names for them: partial dependencies, approximate dependencies, relaxed dependencies. So one common way of thinking about them is these are dependencies that don't hold perfectly. They hold on all records except for 10. There are 10 violations, or up to 10 violations. Then we're going to accept, saying, well, data is going to be dirty. I'm going to expect at least, or up to 10 errors in the data. So any dependency that I detect that is violated by up to 10 records, I'm going to accept as probably true anyway, right? And actually, this is very useful, because if you accept it as true, then you can go ahead with data cleaning, because then you know the violations. Then you know, okay, these records violate the dependency that I like, so then you can go in there and clean the data, right? So as soon as you know a dependency is true, or you've decided it's true, you can look for the violations, right? So you can do data cleaning, right? Or you say it's true for at least 80% of the tuples, or it's true for at least 1% of the tuples. There are different ways of thinking about this, right? There are other ways of relaxing. So for functional dependencies, we, for instance, say if two customers live in the same zip code, they have to live in the same city, right? But you could also relax this and say, if the zip code is similar, then they have to live in the same city. Or if the zip code is the same, the city name should be similar, but we're going to allow typos, for instance, right? That's also a possibility to relax this strict dependency definition. And if you're there, if you have a partial dependency, one that is true almost always, maybe you can go a step further and define a so-called conditional dependency. A conditional dependency is one where you add a condition and say, if this condition is true, then that dependency holds. So you could say, social security number is unique for all customers from the US, right? So the condition is, country equals US, and the dependency, the constraint says social security number is unique, right? While maybe in other countries, it's not unique, or Canada issues social security numbers that might overlap with the US social security numbers. So it's a partial dependency. It's true for some subset of the data, but better yet, I can define what that subset is. So it's a more valuable insight. And again, there are discovery algorithms for these, right? And my colleagues from Salerno put together a survey with all kinds of relaxed dependencies, right? So you can see it's a huge research area. Each of these is one type of relaxed kind of dependency, sequential dependencies and matching dependencies, et cetera, et cetera, et cetera. So there's really a lot here. Of course, don't worry, we're not going to go through these. Just so you're aware, you can go wild in this area. Okay. So as a motivation, what can we do after we've discovered dependencies? Right? There's a whole bunch of use cases. Some of them we'll look into more detail. Yes, Divesh?
So you mentioned all these dependencies. For the students in this room, is there code available for most of these things that they can use, play with?
Yes. I'll get to that later, but absolutely. So I'm really a very strong advocate for open source and open data, and I'll show you later or point you later to a tool that we've been building, Metanome, that includes all our algorithms, but also lots of other algorithms, right? And they're all combined in this one tool, and you can indeed play around with it. And indeed, many researchers worldwide have been using this and adding their own algorithms, et cetera, et cetera. Yeah, it's a lot of work maintaining such a repository, but it's worth the effort. I mean, it's good for research. It's also good for your own research. This is a good tip, for you guys. Don't avoid re-implementing other work if you need to and comparing against it. It will pay off towards the end of your thesis, because then you can easily do lots and lots of comparisons, right? And it's very convincing for reviews. So I've compared against 10 of these algorithms, right? And I'm better. That's very, very convincing. So it's really worth the effort. And you learn a lot, obviously, by doing this. Okay, so what are use cases? A very nice use case is query optimization. This is a purely database kind of problem. Database systems, they want to optimize complicated queries. And the more a database knows about the data, the better it can optimize things, right? That you can find optimal query execution plans. I'll show you some examples later on. Data cleansing, I've already briefly mentioned, right? So basically, a dependency is a rule about your data. So then you can always check, is this rule still true? What are the violations? And I can clean the data. This is a very traditional use case. And actually most of the commercial data profiling tools are sold in the context of their data quality suite, or the data cleaning suite. So if you think of Oracle and IBM and Microsoft, they all have data profiling tools, but they're usually packaged together with the data quality things. Okay? Data integration, I already mentioned, this idea of inclusion dependencies for data lakes. So you have a whole bunch of tables. You want to figure out how do they fit together? How can I join them? And inclusion dependencies are a good hint on how to join disparate tables. What else? I'm not going to go into all of these. Actually, there's a whole research area that I discovered only a few years ago, database reverse engineering, right? Here's a database. What was the ER diagram for it? So what was the original model for this data? Can I extract that from my raw data, in essence, right? So obviously, data profiling helps there as well. So let's have a look at some tools. Again, I'm not going to show you lots of tools. I'm just going to show you in general. First of all, I want to convince you there exist these tools. These are all, we're not going to read through them or anything, but these are all tools that are dedicated to data profiling things. And I did a huge survey together with a PhD student. We looked at 7 of them and looked at the features that they provide, right? So this slide is really to convince you this is a real thing. This is not Felix inventing a field or something. These are all tools. They do all sorts of cool stuff. And you can see they are in this area of data cleaning, data structuring, data discovery. They, this kind of makes sense or fits to the use cases that I mentioned earlier. Okay. And as I said earlier, they're packaged with this cleansing software. Okay, so let's have a look at these feature lists. So again, we're not going to read through all of them. This is extracted from those tools, right? So we don't have to look at all of them. Some of them I like. What do we have? I mean, there are more, right? It just goes on. These are single column ones overall. These are multi-column ones. So you can see percentage of null values. Oh, this one is uniqueness. How unique is a column? But also constancy. I've never heard of that word. So the constancy of the column is the question of how constant is it? So, and indeed, you have many, many columns. And if you just download a whole bunch of stuff from the web, you'll find, this is our experience, about 10% of all columns are constant. They're completely useless in a sense, right? They just contain ones. The entire column just contains the number 1, for instance. Happens a lot. Usually, if the designer over-designed the schema, said, oh, we need this attribute, we need this attribute. Actually, there's no data to fill it, so you put in the default value, let's say, or so, right? So that happens a lot. So there's a measure for that. It's called constancy, right? Pattern discovery, Divesh, is what you said. Regex patterns, or just more simplified patterns like this one here. And then on the right-hand side, the more complicated issues, and there are not many tools that provide this in a proper way. This is easy. This is counting, in essence, right? Well, this is really discovery, looking at data, looking at column combinations. And you can see, as I said, inclusion dependencies, foreign key discovery, functional dependencies, etc. Let's look at one. Okay, Shazia, go ahead. Oh, I'll get to that in a second. So the Benford law is my favorite thing, and I'll show that to you in a second. It's a lot of fun. Some of you are smiling because you know this. And so this is something that's also part of typical tools. They analyze whether data behaves according to Benford's law, and I'll get to that in a second. Okay? But let's get to the more mundane part first. So this is IBM's information analyzer. This screenshot is from their documentation, so I'm not disclosing anything. Just to show you how complicated life can be, right? Just imagine a user trying to use this. So what happened, right? So, I can hardly read this myself. You have this choice here. You go into column analysis, right? And then you select your data source, then you select your table, the employee table, this kind. You don't have to read this really, right? Just follow me. And then there's some summary here, and then you view the details. Then you select the salary, right? And then finally, it tells you a little bit of information about salary, namely that it's 100% decimals and whatever, and the range and stuff like that. So that's data profiling tool for you. I mean, sure, right? It's quite complicated. You have to dive down yourself, but okay, this is a little bit of data profiling. They go a little bit further. Again, same tool from the documentation. So there we're still in the employee table, and we're in the a foreign key analysis, right? This is the foreign key analysis. So you're wondering, is there a foreign key with some other table? So what do? You go into the analysis details, then you choose your base column, employee number. Again, I'm sure you can't read it. You choose your base column, you choose your paired column, and then you hit a button, run. And then it will show you this analysis with this nice little Venn diagram, in essence telling you how many of the managers are also employees. Is this a good foreign key, right? And apparently there's one manager who doesn't have an employee number. Might be a data error, whatever, okay? So what is the problem with this approach? What do you not like about all of this?
I think you kind of need to have an understanding of what you want to look for first without the data just like automatic discovery of
Right.
where those patterns are.
Right, exactly. So you're checking something, but you're not discovering anything really, right? You have a suspicion that might be a foreign key. Is it or is it not? Exactly. Anything else? I mean, there's no errors here. It's okay. I mean, it's a tool. They sell it. They make money of it, I presume. So my other argument would be it's quite complicated to use. I mean, you have to do a lot of things to get where you want to go. It's not like you push a button and you get cool information, right? So usability is a problem. Complex to configure. Scalability, which you couldn't see in this figure, is a problem because they do this checking with a SQL query. Okay, we'll get to that in a second. So SQL is great. Databases are super fast, right? But a SQL query is too much to answer this particular question, is this a foreign key or not? You can do that much, much faster with a cool algorithm. Okay, so SQL is not the best choice. Of course, they use SQL because that's part of their ecosystem, and they're not going to, invent new algorithms and stuff them in there if they can just as well do it with a SQL query. They can, but it's not very fast. And this might be an example or reason why the examples are so tiny with 40 employees and 9 managers, right? And not 40 million employees or 40,000 employees. Okay. So efficiency is a problem. And you'll see later on when I show you some measurements, we're talking about problem complexities that need overnight. I mean, we've had algorithms run to discover things that ran for 2 weeks, and then you get the result. So that shows you maybe how bad we are at coding, right? But it could also show you how complicated the problems are that we're trying to solve. And I hope it's the latter. Okay? So it's restricted to really simple tasks, single columns. So this is one column compared to one other column. They don't do multi-column. And the profiling results you have to interpret yourself, of course, right? So, okay, so why are database management systems and SQL queries not a good idea to check for a foreign key? So what we're doing here is we have one column and we have another column, and we're asking ourselves the question, is the set of values in this column included in this other set? So you can define a SQL query that does this check in essence, right? So what could you imagine? I mean, you have to know a little bit of background about how a database works, but why might SQL not be a good idea here? Kind of an advanced question, I realize that, but maybe somebody has a good answer. So remember, we're trying to find out, are all values of one column included in the other one? It's a Boolean question. I just want to say yes or no. Okay, are you raising your hand?
Is there too many combinations to check?
Yes, so there's a lot to check for sure. You don't have to really check for combinations. What you in principle have to check is for each value in this column, is there a counterpart in the other column, right? But what a SQL query will do, and if we've tried many variations, it will check for every value here, against every value here, do the join between those two columns in essence, which sounds fine, but we're just trying to answer the one single Boolean question, are all values included, yes or no? So you can stop at the first counterexample. As soon as you find a value here that's not included in here, you can stop. It's not a foreign key. You might as well stop. But try teaching a database to stop its query processing, right? And we've tried, at least with SQL, and it just doesn't work. They don't pick up on this. least this is our experience, right? So that's a problem. The other problem is we're just checking one column combination. There are many column combinations, so you'd be issuing many SQL queries. So here we're checking whether manager is a subset of employee number. We could also see is the, I don't know, CEO or C-level employees, are they maybe a foreign key? We're doing that for every column, issuing the same query again and again. So of course there are good algorithms that will just do all of that in one go instead of issuing 20,000 SQL queries. Okay. And then of course this last one here, interpretation of the results, this is the big question here. This is going from pure algorithmic things to semantics, to understanding, right? And so there's some research in this area. Is this really a foreign key or is it just a coincidence? I'll give you one example. Employee numbers, they start at 0 and they just count up to, I don't know, 25,000. And another column is a Boolean column with zeros and ones. Of course, that column is included in the numbers from 1 to 40,000, but it's not a foreign key, clearly, right? So how do we understand these kind of questions? So that's one of those typical examples where you get a wrong candidate, right? It's an inclusion dependency, but not a meaningful one, right? Okay, checking versus discovery. We already talked about exactly this, right? I mean, this is nice, right? This is a tool here saying cross-table analysis enables you to identify matching or orphaned records. This is exactly what we're trying to do between two tables based on a fully customizable join condition and optional filter on either table. What they're telling you is you have to do it yourself. That's what they're telling you, right? Okay. Good. Okay. So why is this a difficult problem? Scalability is the issue here. Right? So scalability in the number of rows is clear. If you check something, you have to go through all the rows to check whether something is true. This is clear. But the number of columns is really the problem here. So, if you have a table with 100 columns, which is not unusual, right? There's, as you can see, 1.3 nonillion column combinations. Okay? It's a crazy number. And obviously, you will never, ever going to be checking anything anywhere near 1.3 nonillion candidates, right? So we have to avoid this, and this is what you do algorithmically, right? So any column combination could be a key candidate, just to give you one example, right? And so if you want to find all key candidates, all unique column combinations, in principle, you have to check all column combinations, whether they have the key property, yes or no, right? And that's the amount of work you should be doing, or you shouldn't be doing, but you might be doing if you're doing it not in a good way. Unfortunately, the problem gets worse. Even the solution space is exponential in nature, right? There can be an exponential number of unique column combinations in a given data set, exponential in the number of columns. So you can see this lattice here. We'll be seeing more of those as the tutorial continues, right? This is a representation of all combinations of things. So these are the individual columns down here. And the next level are pairs of columns, right? And then triples of columns, et cetera, right? And in principle, this middle row here could all be individually minimal unique column combinations. And with really bad luck, that's your solution. And so even enumerating the solution might take very long. And Divesh, I know we've developed some cool techniques to have a more compact representation of this very large space. But for the sake of simplicity, I will be skipping this. Okay, good. Okay, so for the last few minutes of this section, we'll look at basic statistics. Okay, this is exactly the minutes that you took for your introduction. I'm a little bit over time. So the easy stuff, as we mentioned earlier, so data types. So you have one column, right? And you look, the easiest thing to do is this a string or is it a numeric column? And often we want to do that because we treat them completely differently usually. Right? For numeric columns, you can look at correlations and all these kind of things. Then you could do a little bit more advanced and distinguish dates. Dates look like strings, but they can be treated quite differently, and they're usually easy to recognize, right? You could also try to distinguish between categorical and continuous values, right? So even if you have, the numbers 1 through 7, those might be weekdays and not actually numbers 1 through 7. Right, you could try to distinguish that. Then you could go on and find SQL data types, for instance, which are even more fine-grained. You have a Boolean type, you have a date type, you have timestamps, you have varchar 25, and you could just do more fine-grained analysis. You could look for entire domains. You could look for regular expressions, or even semantic data types, as in fax number, email address. They're all strings, right? But you could try to find out, is this a specific domain? right? This is all nice. And then we have, as I mentioned, these cardinalities. I'm not going to read through them, but I'll get back to Shazia's question. Benford's law, also known as the first digit law. And we'll look at this right now just because it's a little bit of fun and I love to show this. So who's heard of Benford's law or the first digit law? I mean, you've heard of this or you know what it is. Good. Okay, great. Divesh, I'm sure as well, because he's heard. You have to suffer this talk maybe at least twice already. Okay. Okay, good. So Benford's law is actually a misnomer. It's not really a law. It's kind of a property or an observation by the statistician Benford. It's also called the first digit law because it says something about the first digit of a bunch of numbers. So if you have a number and it has a first digit, right? It's never the 0. I mean, you don't start a number with a 0. It could be 1, 2, 3, 4, 5, 6, 7, 8, 9. And the statement that Benford makes is if you look at a bunch of numbers, usually they start with a 1. And if they don't start with a 1, it's more likely that they start with a 2 than anything else. And if they don't start with a 1 or 2, then probably they'll start with a 3, etc. It's crazy, huh? I mean, it's really a little bit mad. So formally, you can say this property basically says the distribution of a number, corresponds to, that formula. It's a logarithmic property, and it holds, and you can easily see that if log x is uniformly distributed. So you have a bunch of numbers, and if you take their logarithms, and if those numbers are uniformly distributed, then Benford's law holds. So you can think of it that way. You see this log scale here. If you randomly choose points on there, right, then usually, this whole area starts with a 1, this whole area starts with a 1, right? That's the largest areas. For the 3, just starts for this small area and this small area, right? So this is exactly what we're observing here. Now, of course, the big question is, why should this be true, right? This is an interesting property, but why on earth should it hold? Well, Benford went about and just tried it out. He looked at all these numbers. He looked at surface areas of rivers, molecular weights, 5,000 entries from a mathematical handbook, right? I like this one, street addresses of the first 342 persons listed in American Men of Science. This is how you did empirical research then. You opened the big book of American Men of Science and looked at the addresses, right? And then, by the way, for the sequence of 2 to the power of n, this also holds true, right? If you just look at the whole sequence, usually it starts with a 1. Not at the beginning, but later on, there are more 1s, don't worry, okay? So I took this example. This is a nice one from Wikipedia. It looks at the heights of the 60 tallest structures. Chimneys, high-rises, TV towers, antennas. These are all structures, and the 60 tallest structures are listed in this table here. And the leading digit 1 appears 26 times among those 60, so that's 43%. Benford said it should be 30%, so it's not exact, of course, it's only 60 numbers. But you can see that this distribution is actually pretty close to Benford's law. Right? These are the tallest structures from Wikipedia. And the coolest thing is, it doesn't matter if you're measuring in meter or feet. So the unit doesn't matter. Yeah? It's pretty crazy. Okay, I'll give you another example. Divesh already mentioned that we work a lot with Wikipedia and tables in Wikipedia. And we extracted, millions and millions of tables from Wikipedia, looked at all the numeric columns, and lo and behold, this is what we counted as leading digits, and this is what was expected. So all of Wikipedia together also follows Benford's law. Okay, and then here's the kicker. I did this, I love this. So this is the page of NIST, all physical constants. Over 100 physical constants, like the Planck number and stuff like that, right? And again, they follow Benford's law. It's pretty wild, huh? So this property is actually used as evidence in court proceedings. The idea is just the following. Naturally occurring numbers that cross many orders or several orders of magnitude, right, often follow Benford's law, right? So if I look at the ages of the people in the room, you're not crossing many orders of magnitude, but Benford's law will not hold, right? If I were to look at your salary, I don't know if that goes over many orders of magnitude. It might, right? Or several orders of magnitude. Then you often have this effect, right? So for instance, if you start your salary with 100 and it doubles every year, this is an exponential growth, be nice, right? The first year, all your salary is always going to be, on every day, it's going to be 100, 101, 102, etc. And on the final year, at the end of the year, you get 200 salary. And then it doubles every year, so then it's 400, and then 800, and then you're very quickly back to 1,000, and it will last quite a while along that 1,000 something, right? And so if you're crossing orders of magnitude, often you see this effect. Of course, it's not a law, but it's a very frequent observation. And if you're making up numbers, you're fudging numbers in your Enron company or so, right? And you don't know of Enron's law, your numbers will not follow Benford's law, and that's very suspicious. Or if you do this too exact, that's also suspicious. So somebody told you about Benford's law, you say, ooh, I better do it exactly like Benford's law tells me. It's also a little bit suspicious, right? Okay, so any tax gains that you get, I get 10% after this lecture. Yeah, so now you know how to cheat properly, right? Okay, good. So with this, I think we can do a 10-minute break, or what is the idea? I forgot. Anyway, a break.
Come back at 2:30.
2:30? Okay. So thanks for your attention, and I'm around, and see you back in a few minutes. There's one question.
Not a question, just a comment, right? This is an empirical observation.
Yes.
Right? So a different problem, which is sort of, if I look at the last digit of a prime number, right? And I think of it, what is the distribution of that? This year, there was a person who got the equivalent of the Nobel Prize, the field dependent mathematics. Part of the reason was showing that the distribution of the last digit of prime numbers
Yes.
is uniform if you take it to meter.
Yeah.
Right? He proved it.
Yeah, okay. So the last digit, just to repeat it for everybody, the last digit of all prime numbers, if taken to infinity, is uniformly distributed. Yeah, I mean, prime numbers are always strange, of course. I could add, though, to this, there's also the same law holds for the second digit, and for the third digit, just weaker. For the first digit is pronounced, the second digit also has a distribution, just not quite as strong. And then the last digit is the weakest, I guess. Okay, so see you soon.